Hello everyone, and welcome to the first Wallet Making Wednesday. Today we're going to be making this G10 composite part, which is the base plate for our Archaeo magnetic case wallet. Let's jump into Fusion. Okay, before we jump into the cam, we're going to take a look at the complete reference design and the model view of the magnetic case wallet, just to get a better idea of what the purpose is behind some of the features that we're going to be milling in this part. So here we have the top plate of the wallet, two binding posts, a front flexible veneer insert, a credit card stack, the back insert, and if we flip the wallet around here, we have a better view of the part we're going to be making here. So here we have the modular back lid with its 4 screws, two binding posts inside recessed cavities for the internal spring compression system. We have our magnetic latch that pivots open. So if we start removing some components here, we can take a better look at the model. So remove the lid, remove the latch. So here's the back view of the part. So some pretty cool features in here that we're going to be doing the cam for. We're going to be using everything from 2D contours to 2D and 3D adaptive clearing. We have 4 holes here for pressing threaded inserts into. We have 3 holes to be drilled for N52 neodymium magnets, and this is our latch pivot where a 632 screw goes in, separated with nylon spacers to reduce friction. Okay, so that's a basic overview of the part we're going to be milling. We're going to be using a 10mm stock G10. And this entire wallet is made out of G10 or our carbon fiber composite, which have very unique properties when you're milling that are quite different than milling metals like aluminum or brass. So let's take a look at our palette here. Okay, so this is our palette of 8 base plates. So we're going to quickly jump into the cam now. Okay, so now that we're in the cam, you'll see that there's all these red exclamation marks. Whenever you load a Fusion file, that tends to happen, so you just have to reload the toolpath. So I'm just going to click on the setup and just hit Control G to generate all. It'll take a moment, but now that they're all generated, we can take a look at these toolpaths. Okay, the way I like to go about milling a part like this is to start with any drilling or boring operation and then move on to the largest pocket or feature you have for that particular tool you have selected. So we're going to start off with our counter bore operation for our recessed spring tensioning system here. So this is a 2D contour. We're going to be running with a 1/4 inch diamond coated Burr end mill. Because this is G10, it has very different cutting characteristics than a metal like aluminum, brass, or steel. Our chip load, or our feed per tooth, we can essentially completely ignore this because this material does not produce chips, it produces dust. And since we're using flood coolant, it kind of turns into a sludge. So it becomes very important to have a nice, strong flood coolant blast to clear out that sludge as it's made in the cut. So I'm going to go pretty quickly through these. We have about 20 tool paths to get through. So we're going to start by selecting the bottom of these recesses, making sure that our selected contours for our bottom height is selected. Our passes, our radial stock to leave and axial stock to leave, are determined basically by experiments or how many times you've made this part, getting it to fit your tolerances based on the reference model, you can adjust your radial and axial stock to leave. Now, because we're following this contour in here, our wrapping angle is set to 5 degrees. Our lead in and lead out are disabled. So let's hit OK. Alright, so that's our tool path. You can see that it starts probably a millimeter or so above the part, or the stock. So by the time it hits the stock, it's already into the tool path. Okay, so our next operation is going to be our 3D adaptive roughing strategy. So we're going to clear out this main pocket in here. Same tools before, 24,000 RPM, running a bit faster at about 40 inches per minute. So our geometry tab, we're going to make sure the machining boundary is on selection. We're going to select the inside contour here. And for our model, we're going to select the front face. And our tool containment is inside boundary. In our heights tab, the main thing we want to be concerned about is the bottom height. That's just going to be our model bottom or our stock bottom. Move over to our passes tab. Now this is the most important tab here because this is where you set your optimal load, which ultimately determines your material removal rate. So for G10, it's going to be 2.5 millimeter step over. Now our stock to leave, because this is a roughing strategy, we're going to leave 1 millimeter in our axial stock to leave. In our linking tab, the main features here you want to be concerned about are your stay down level. We're going to make sure that's on least to eliminate how many z-axis movements there are up and down while it's in the operation. Our lift height, which is how high we want the tool to move above the cut in between paths. Our non-engagement feed rate, this is typically your whatever your G0 rapid is for your machine. So with our Openbuilds C-beam machine here, we have it set to about 2,000 millimeters per minute. Your lead-ins and transitions are typically a derivative of your tool diameter, so you can typically leave these as default. Now your ramp, I like to keep this fairly shallow when we're cutting G10 this fast, so especially because we're making a full 9 millimeter depth of cut. Our ramping angle is going to be at 2 degrees. Just hit OK and generate that. Alright, so that's our main 2D or 3D adaptive strategy. So we can see here that in these corners the tool doesn't go all the way around these fillets. So we're going to have to use manually selected 2D contours to make sure that all the parts or all the features are milled properly, as well as this front area here. We're going to be using 2D contours to clear that out. So next we're going to go to the left side of the wallet with a 2D contour. Again, same tool, 24,000 RPM, same speed. Now our geometry, we're going to, instead of selecting the entire thing, if you hold down the Alt key and then click, you can select each open contour individually. So there's 4 open contours selected, and we want to make sure all these arrows are on the outside of the tool, not on the inside. Now for our bottom height, we want to make sure selected contours is selected. That should be the default. In our passes tab, this is where we set our depths, so we want to take some nice quick shallow passes. So in multiple depths, we have 2 millimeters as our roughing step down. Use even step downs, and we want to rough our final. Now in our linking tab, we want to make sure our lead-ins and lead-outs are well thought out. So we want a nice shallow lead-in before approaching this fillet, and a nice shallow lead-out without cutting into the main stock. So we have 20 degrees for our lead in and 0 degrees for our lead out. Let's hit OK. Alright, there it is. Alright, and since we're on the left side of the wallet here, we're going to continue on and clear out this pocket. So in our pivot pocket operation, this is a 2D adaptive strategy. Same RPM, 24,000. Same cutting speed at around 40 inches per minute. Move over to our heights tab. Our bottom height is going to be our selected contours again. So in selecting our geometry, this is always kind of tricky for a part like this. So what I do is I select the inside contour, and then I move to stock contours and select the entire area around where I want to machine. Our passes, we want to take this in about two depths, make sure it's nice and accurate. So we're going to have 3 millimeters as our roughing step down, and our stock to leave, again, is just completely experimental based on how many times you've run this part and what tolerances you like to have based on your feed rates. In our linking operation, our lead-ins and lead-outs aren't terribly important because we had just previously cleared this area with our adaptive and cleared this area with our 2D contour. So there's really not going to be much to lead out into. So it's going to hit OK. Again, you want to make sure your stay down level is on least and your non-engagement feed rate is high. Alright, so that's our 2D adaptive strategy to clear that pivot pocket. Again, since we're on the left side of the wallet, we want to continue and clear out this front area here that our previous adaptive strategy didn't touch. So we're going to use a 2D contour. Same tool, same RPM. We're going to hold down the Alt key and select this front contour. We're going to make sure, so because we have a 1/4 inch diameter tool, we want to make sure that it doesn't plunge into the stock material, so we want to make sure to move that contour over, as well as on the end of the contour, we want to move it away from this fillet. So we're going to have -2 millimeters for our tangential extension distance, making sure our arrow is on the inside. We're going to make sure our bottom height is selected. We want our selected contour selected with a 1 millimeter offset to match our axial stock to leave on our previous adaptive operation. In our passes, we want to take off another 3.5 millimeters from the end, just to make sure there's enough clearance. So we're going to hit OK. And we can see the very basic tool path. Okay, now our next operation is going to be a continuation of the previous one. We're going to continue to clear material out here to make room for our finishing pass for this main pocket later on. So it's just been duplicated from the previous operation. Same tool, same feeds and speeds. We're going to select the exact same contour holding down the Alt key, except this time we're going to click this red arrow and move it to the other side. We have no tangential extension distance on this one. Our bottom height is going to be our selected contour. And we have a tangential fragment extension distance of about -1/4 inch. We're going to take this in about 3 cuts, so 3 passes, so our maximum roughing step down is about 3 millimeters. Just basic lead in, lead out. Hit OK. That's our tool path there. Next we're going to machine this fillet out here, because our main pocket only extended to about this point. Same tool, same feeds and speeds. Now for our geometry, we're going to select the top of this open contour, holding down the Alt key, and click. Our arrow is on the proper side. I added 2 millimeters for our extension distance, just to make sure it gets all of that fillet and doesn't end, so leaves a little piece of material here. We want to make sure we go all the way through. Our heights, because we selected the top of this open pocket, our bottom height is going to be our stock bottom. And it's fairly, at this point, it's kind of arbitrary about what my axial depths are, because I'm going to be doing a finishing pass for this entire area later on. So our passes are going to be similar to our previous operations, 2 millimeter step downs, and basic lead-ins and lead-outs. Alright, let's go ahead and click OK. There we go. So we're next going to mill out this open pocket here for our N52 magnet. Again, it's another 2D contour. Same feeds and speeds as before. Our geometry selection is pretty simple. Just click that one right there. It's on the right side. Now our tangential extension distance is a little bit higher this time, because I want the tool to plunge down and be at the axial depth of the pocket before it starts moving into the material, just so I get a nice sharp corner here. Our heights, our bottom height is our selected contour as default, and our maximum roughing step down is 2 millimeters. Hit OK. There's a little bit of wasted movement here, but overall it really doesn't make that big of a difference. Alright, now we're going to start pocketing out this top portion for our bottom lid. So we have another 2D contour operation here. We're going to be a little bit slower on our feed rate than before. We want to get some nice accurate cuts on these outer contours of this pocket. So let's start selecting our geometry, holding down the Alt button. And then the top. Making sure that all of our arrows are on the inside. Alright, that looks good. Now we have a little bit of a tangential end extension distance. Our bottom height is our selected contour, so that's good. And our stock to leave adjustments. Our feed rate optimization is about 50% of the feed rate as our main cutting feed rate, and we have our feed radius at a nice high value to make sure we get this shallow curve here. And our standard lead in, lead out. Let's hit OK. Alright, that looks good. Nice and slow around this top curve. Slows down as it enters this curve. So this is the outside portion of this open pocket. Now we're going to start on the right hand side with another 2D contour and mill out this remaining area here. So we're going to run this one a little bit faster, because now we're just clearing material, 800 millimeters per minute. Let's select our contour. And because we've already milled this area here, we can leave about 5 millimeters or so. So our step over is 5 millimeters with the number of finishing passes as 2. Our radial stock to leave is 5 millimeters. So that means we're going to start this contour 5 millimeters away from this line. and then each step over is going to be 5 millimeters after that, and we're going to have 2 of them. So let's hit OK. That should nicely take care of the rest of this material up here. Now we're going to duplicate that same thing on the left side with another 2D contour operation. .800 millimeters per minute. We're going to select our geometry, holding down the Alt button because we want to make sure we just get these little sections, not the entire contour. Our arrows are on the inside, that's good. Checking our bottom height is our selected contour. And our passes, just like on the right hand side, we're going to have 5 millimeter radial stock to leave with a 5 millimeter step over with 2 passes. So let's hit OK. And that takes care of the rest of this lid pocket. Okay, now we're going to do the finishing pass for our main open pocket here. This is a 2D pocket operation. Same feeds and speeds as our previous 3D adaptive. So we're going to select, just click anywhere on this open face. Our bottom height is going to be our selected contour, so that means it'll be right on the model surface. Click our passes tab. We want about 4 millimeter step over, so that's about just over 50% of the tool diameter. Our stock to leave, we're just going to take a little bit off the top and a little bit off the side. Our feed rate optimization is important here because we don't want those corners to be very sharp. So we have 600 millimeters per minute, or about 40% less than our cutting feed rate. This basic lead in, lead out, not too large, so we don't want to cut away too much stock on the outside of the part. Let's hit OK. Alright, so we're going to remove that axial stock to leave just so you get a better view of the tool path. So that's our finishing pass for our main pocket. You can see the reason for these previous 2 2D contours was to remove enough material to give this finishing pass enough room for its lead in. Alright, so that's all the main features and pockets milled out on the front face of this part. So now we're going to cut out the outer contour. So we're going to run fairly quick at 40 inches a minute or so. A nice easy plunge rate. So let's click our geometry here, the entire outer surface. Now in our tabs, we're going to make sure we're in at points instead of by distance, so we can specify exactly where we want them. Easiest way to do this is to go right on the top view, and then just click anywhere on the contour on the right and the left that you want to have your tabs. You can notice here that even though I click on the top contour here, it knows to put the tab on the bottom. And right after we set our tabs, I like putting an entry point right on top of one of the tabs, just like that. Now we're going to be plunging down 2 millimeters underneath the stock bottom to make sure we get a nice edge finish. Move over to our passes tab. We're going to be taking 3 millimeter step downs, and our feed rate optimization Our feed rate optimization, we want to be about 40% less than our cutting feed rate, with a radius that's large enough to get these high radius corners here and in here. Now we're going to hit OK and generate that. So you can see here there's two paths here. Our finishing pass is slightly to the inside of our other passes. We do that so we get a nice clean edge. So the way we go about doing that, let's go back into our passes, top view. We have our roughing passes selected with one step over. And then this maximum step over just needs to be more than how much you want your finishing pass to be. So as long as this number is more than this number, it doesn't really matter what this is. So our step over is going to be 0.5 millimeters. So that means it's going to leave 0.5 millimeter on all of the step downs except for the final one. So on multiple depths, we have finish only at final depth selected and use even step downs. If we weren't going to be doing it like that, we would just click rough final and it wouldn't need to take that path. Alright, so let's hit OK again. And that's our outer contour done. So now we're going to go ahead and chamfer the outside edge of our part here. We're going to go a little bit slower than our outer contour. We're at 600 millimeters per minute. Now our geometry, we're going to have to do a lot of manually selecting because it wants to just select this entire contour here. So we're going to go in close and hold down the Alt key and start selecting our contours. Right, that should be all of them. Now because we have a spot drill type of tool selected, we're going to have some extra options in our passes tab. Now I like to actually keep the model at 90 degrees. I don't put the chamfer in the model just because I find it gives me a little bit easier way to experiment with the different tip offsets and chamfer widths than if I had the actual model chamfered. It's just personal preference. You can have the model chamfered or not, but for chamfer width you typically want to have the bottom chamfer selected, and then the chamfer tip offset is the distance from the bottom of the chamfer to where the tool will actually be as it goes around the part. So I have a nice healthy 0.5 millimeter around the outside with about a 1.7 millimeter chamfer width. So we're going to hit OK. And that's our chamfer. So we're going to do another tool change and start processing these holes. So we're going to be using a 1/8 diameter titanium nitride coated Burr end mill. We're going to start with our binding post, boring operation inside the these recessed pockets for our internal spring tensioning system. So this is a 2D contour operation. I just selected the two contours I want to machine. Now our heights tab, our top height, we want it to be the selected contour. Now because we've already milled out this pocket in here, for our top height, we can actually rapid all the way down to 1 millimeter above our selected contour. And then for our bottom height, just to get that nice edge finish, we're going to be taking out 2 millimeters underneath our stock bottom. So we're going to hit OK. And you can see here, that's our nice rapid down into the hole to save time. And we're going 2 millimeters underneath. Next, we're going to be doing our latch hole. So this is a drill operation. Our cutting feed rate is going to be 600 millimeters per minute. Our plunge is just going to be default. Geometry, just select the face. Our heights, making sure it's drilling down 2 millimeters underneath the stock bottom, just to get that nice edge finish again. And our cycle, we select bore milling, climb with a 0.5 millimeter pitch with a hole diameter of 3.75 millimeters. Just because I want to give those 632 screws enough space without being too tight. Let's hit OK. Next, we're going to be doing our threaded insert holes. So, same tool, same cutting feed rate. We're going to select our geometries. Now, the great thing about using the drill operation instead of the bore, which is you can also use this operation here under 2D. But with if you use drill and select bore milling, you can specify whatever diameter of hole you want. So in this case, I experimented with a number of different threaded insert diameters, and all I would need to do, instead of having to go in and change the model, awkwardly I could just change the diameter right here in the cam. So we have a diameter here of 6.5 millimeters, 0.5 millimeter pitch. Let's hit OK. Next, we're going to start boring our magnets, our magnet holes. So here we have this one selected, 4.8 millimeter diameter with a 0.5 millimeter pitch. Let's hit OK. And that does it. Next, we're going to be doing these magnet holes here for our key organizer attachment. So again, 600 millimeters per minute. Let's select our geometry. Now our heights are a little bit interesting. I have this tweaked a little bit. The top height, I want to make sure I don't plunge too far into this material. Because as you can see, if I did a simulation, you would see that there's still material covering this here. Because when we were milling out this 2D contour for this lid, we didn't go far enough to cover both of these holes. So we're going to give a nice generous top height, so 5.5 millimeters above the hole top, to give us enough room to clear whatever material might be remaining in this location. Hit OK. Our final operation is to mill out this pocket, and it's just going to be a simple 2D contour. So same tool, very simple geometry selection this time. Whoops. Just like that. Our arrow is on the right side. Now we're going to mess with the passes a little bit. We're going to do 2 finishing passes with a step over 2.5 millimeters. So that's just under 1 tool diameter. and we're going to take a 2 millimeter step down for each pass. And our feed optimization, because we want this to be as accurate as possible, because we're going to be sliding in the key organizer and we don't want it to be wobbling around, we're going to have a reduced feed rate of 200 millimeters per minute with a radius high enough to be able to capture all of the corners. So let's hit OK. So we also have a nice shallow lead in, so we're not accidentally making any marks on the outside of the part. And we accelerate on a linear portion, and as we move into the corner, that's when the feed rate optimization kicks in, so we get that nice sharp corner. Because this is a DIY CNC machine, it's not like a Tormach or a Haas or anything like that. We have to be very mindful of our feed rate optimization and our tool deflection. Okay, so that's the final operation of this Archaeo magnetic case wallet base plate. Before we post this to the CNC, we're going to quickly simulate just to make sure there's no collisions. And if there are, see if they're really valid or not. So we're going to make sure we're in tail to make these tool paths easier to see. And I can see that we do have one collision warning here. So we're just going to drag the cursor over just to check out the tool paths quickly on the way there. Okay, so let's slow that speed down. Let's see if this is really an issue. It doesn't look like it's really colliding with the stock in an abnormal way. This might just be an error due to not having a lead out distance specified. So we're just going to safely ignore that and continue on with the simulation. Okay, that's the end of the simulation. Everything looks good and ready to post to the CNC. Thanks a lot for watching, and I hope you're able to learn something valuable about machining in Fusion 360. If you have any suggestions, or if you'd like to see me go into depth for a specific toolpath or operation, just let me know in the comments section, and let's jump to the CNC.